In this lecture, we discuss about linearly dependent and independence of vectors. What is the meaning of vectors? A set of matrices satisfy all the properties of vector space are called the vectors. Linearly, now since all the matrices are vector space, therefore we can say that row vector or row metric or column metric as a vectors. Next definition is linearly combination of a vectors. Let x1, x2, x3 up to xn be n vectors and c1, c2, c3 up to cn be n scalars such that c1x1 plus c2x2 plus c3x3 plus cnxn is called the linear combination of the vectors. So there are n vectors, x1, x2, x3 up to xn, n scalar c1, c2 up to cn. Then we write down the linear combinations c1, x1 plus c2, x2 plus c3, x3 up to cn, xn. This is called linear combination of the n vectors. Linearly dependent vectors. The system of n vectors x1, x2, x3 up to xn is said to be linearly dependent if there exist n scalars c1, c2, c3 up to cn, not all zero, such that their linear combinations is equal to 0. So if we say that if the n vectors x1, x2 up to xn are given, then these vectors are called linearly dependent if the linear combination c1, x1 plus c2, x2 plus c3, x3 up to cn, xn are 0, but all c1, c2, c3, cn are not equal to 0. They are non-zero. At this time, we can say that, or at this situation, we are able to say that x1, x2, x3 up to xn variables or vectors are linearly dependent. In the other hand, linearly independent vectors, the system of n vectors x1, x2, x3, xn is said to be linearly dependent if there exist n scalars c1, c2, c3, cn such that their linear combination is equal to 0, which implies all c1, c2, c3 up to cn are also 0. So such type of vectors are called linearly independent. So in case of linearly dependent, if the linear combination of the vectors are 0, but all c1, c2, c3, cn will not be equal to 0. But in case of linearly independent vectors, if linear combination is equal to 0, which means that c1, c2, c3 up to cn, all scalars will be equal to 0. Let us take one example, then it will very clear about the linearly dependent and independence of the vector. Examine for linear dependence and independence of the following vectors. Find a relation among them if they are dependent. We have given three vectors, 2, minus 1, 3, 2, 1, 3, 4, 2, 3, minus 5, 2, 2. Let us try to solve it. We have to examine for linearly dependence of the following vectors. x1 is equal to 2 minus 1, 3, 2. x2 is equal to 1, 3, 4, 2. x3 is equal to 3 minus 5, 2, 2. Let c1, c2, c3 are three scalars such that c1x1 plus c2x2 plus c3x3 is equal to 0. Let us substitute the value of x1. The value of x1 is nothing but 2 minus 1, 3, 2. So c1 into 2 minus 1, 3, 2. c2, what is x2? 1, 3 into 1, 3, 4, 2. And c3, what is x3? It is 3 minus 5, 2, 2, which is equal to 0. Let us again simplify it. We have to multiply this 2C1 minus C1 plus 3C1 and 2C1. And this is the first part. Similarly, C2, 3C2, 4C2 and 2C2. Second part. Similarly, 3C3 minus 5C3 plus 2C3 plus 2C3. Now there are 4 tuples. So adding this plus this plus this, then adding this plus this plus this, adding this plus this plus this, and at the last we have to add 2C1 plus 2C2 plus 2C3, and which is equal to 0. Now 0 means what? It is 0, 0, 0. So if it is 0, what means? It means that 2C1 plus 2C2 plus 3C3 is equal to 0. Minus C1 plus 3C2 minus 5C3 equal to 0. 3C1 plus 4C2 plus 2C3 equal to 0. And 2C1 plus 2C2 plus 2C3 is equal to 0. So we have 4 equations and 3 unknown C1, C2, C3. This is a system of homogeneous linear equation Ax equal to 0. So we can write down Ax equal to 0. A is the coefficient matrix. 2, 1, 3, first row. Minus 1, 3, minus 5, second row. 3, 4, 2, third row. And 2, 2, 2 is the fourth row, which is into multiply by C1, C2, C3, because here the variables are C1, C2, C3, and the constant matrix is 0, 0, 0, and 0. Now here we want to reduce the above matrix, this matrix, to its echelon form by using only the row operation. So first let us interchange, since if you want to reduce into row echelon form, the A11 should be either 1 or all the below element A11 should be multiple of A11. Therefore, we are interchanging R1 and R2. We have this R2 become the first row, minus 1, 3, minus 5, and this R1 will become the second row, 2, 1, 3, 3, 4, 2, 2, 2, 2. Now with the help of this minus 1, we have to make this, this, and this 0. For this purpose, we apply row operation in R2 by R2 plus 2R1, in R3, R3 plus 3R1, in R4, R4 plus 2R1. If we apply this operation, there is no change in the first row. It is as it is. Now for the second row, we have to multiply this row by 2 and subtracting from 2, 1, 3. 2 minus 1 is minus 2. 2, 3 is 6, minus 10. And if we subtract means we have to add them. No, sorry, we have to add them. Therefore, 2 minus 2 is 0. 1 plus 6 is 7. 3 minus 10 is minus 7. So this is 0, 7 minus 7. Similarly, if we apply the second operation, 3, 4, 2, 3, 4, 2, minus plus minus 3, 9. We have to multiply this by 3 and minus 15. If we add them, this is 0, 13, and 2 minus 15 is minus 13. So again, third equation is also okay. Third row is also okay. Now for the fourth row, if we add R4, what is R4? R4 is 2, 2, 2. It will be subtracted by minus 2, 6, minus 10. If we add them, it is 0, it is 8, it is minus 8. So this is the reduced form of the given matrix. Now we come to A22. If we see A22, it should be 1 or all the below element of A22 should be multiple of A22. But here we are getting the negative answer of both the question. Means there is no such type of possibilities. So let us try another way. What we are doing, we are dividing this R2 by 1 by 7. Then we have minus 1, 3, minus 5. And this, if we divide this by 7, 0, 7 by 7 is 1, minus 7 by 7 is minus 1. Now with the help of this A22, we should make this and this 0. For this purpose, we apply row operation in R3 by R3 minus 13 R2, and in R4, R4 minus 8 R2. Then we have minus 1, 3 minus 5, 0, 1 minus 1, and 0, 0, 0, and 0, 0, 0, which is equal to 0, 0, 0, 0. Let us simplify these matrices. Minus 1 into C1, 3C2, minus 5C2, C3, which is equal to 0, and 0 into C1, 1 into C2, and minus 1 into C3. So this gives us C2 minus C3 equal to 0. Here we have three variables, C1, C2, and C3, but we have only two equations. It means that the one variable has independent values. Let us put C3 is equal to P in this 3. We have C2 minus T equal to 0. Therefore, C2 is equal to T. If C3 is T, then C2 is also T. If we substitute the value of C2 and C3 in equation number 2, we have minus C1 plus 3C2 minus 5C3 equal to 0, which implies minus C1 plus 3T minus 5T equal to 0. Minus C1 minus 2T is equal to 0, because 3T minus 5T is minus 2T, or C1 is equal to minus 2T. Since the values of C1, C2, C3 are not all 0, therefore the given vectors are linearly dependent.